Hello everyone. Featuring in expert voice today is Professor Kevin Potter, one of the leading tutors in composite manufacturing.
Hello, I'm Kevin Potter. I'm the NCC Professor in Composites Manufacture, and I lead the composites manufacturing activity in Axis in the University of Bristol. Why did I choose composites? I think the short answer is I didn't. I did a material science degree because when I left school I didn't want to stop doing either chemistry or physics. I've always been a pretty poor mathematician, so I didn't want to do engineering, and material science was a field at that point that was really just starting to open up. At the end of my degree I had 3 job offers open to me, and I took the one that looked the best within a government research lab. I didn't actually know what I was going to do there when I went in there, but what they wanted me to do was to start working on some composite rocket motors. So that was the start of a sort of 40-year experience with composites, and I sort of fell into it, not really expecting to be necessarily doing it. Got the bug, and I've never really done anything else. My main research interest in composites has really been now what they've always been, which is essentially manufacturing. Here is a piece of carbon fibre. It's actually an antique. This is from the first batch of carbon fibre ever made. It was produced in 1966, 50 years ago. And the basic question that all of us in composites manufacturing have had to struggle with for the last 50 years is how do you actually make anything useful like black string? What I've got here, I want to make this into an aeroplane, or a wing, or a wind turbine, or a sports car. And that question of how we can go from a lump of string to a physical component that actually carries load is really what's been driving most of my research for the last 40 years. I suppose what I'm probably best known for in the sort of academic community is the work that I did on understanding how the sorts of reinforcements that we use to make things actually deform so that we can shape them to the sort of geometry that we want. I mean, back in the early 70s it was becoming very clear that the materials that we had, which were basically what was called unidirectional prepreg, which is a whole bunch of fibres in strips parallel to each other, held together with resin. And if you try and actually form it over a surface, it's very difficult to get anything that comes out really well without any defects or wrinkles. It's incredibly skilled work, basically. So what we did at that point was we developed woven materials that were much easier to form to the geometry, but really nobody understood how to predict what the material would be like once it reformed to the shape. So we started some work back in the mid-70s, and by the end of the 70s we'd developed what's called a drape model. It basically allows you to predict where the fibres end up when they form over a surface. I think that was probably the first computer-driven drape model that existed in the world. The problem was, back in the 1970s, there was no such thing as a graphical interface, there was no such thing as graphical output from computers. So we didn't have the beautiful pretty pictures that you now have out of the computer system. All we had was a bunch of numbers. And so it was still quite tricky to interpret those numbers in terms of the way to actually manufacture something. The other thing that I was quite well known for was the development of something called resin transfer molding, which is a method of making components that allows you to make some very complex parts, much more complex parts than you could make in the sort of processes that were conventionally available. These parts here are manufactured by resin transfer molding. These were both made, roughly speaking, 25 years ago, and they're probably at least as complicated as anybody's making today. So to a certain extent, at one level, the technology hasn't really got that much further over that sort of time period. So this, for example, is part of the bypass duct for a gas turbine. So this goes on an aircraft. when you want to go into thrust reverse, these drop down and a series of them block the bypass duct. So this is a very complex part. We have unidirectional fibres that run down here, run all the way back here, run down there and all the way back. So we then pick up the loads on these points here. And these are very, very skinny lugs compared to the sort of lug that you would put if that was a metallic component, or even if it was a conventional composite component. We would have to have a big lump of material there and drill a hole in it because we'd have a very high stress concentration. The loads around the lug would be much higher than they are away from the lug. But because we're using carbon fibre and we're wrapping it around there, we can get down stress concentration factors that run down from a factor of 3 to about 1.2. So that's another way in which they're using the composite materials with their strength related to the alignment and the way that we handle the materials that gives us much more efficient structures than we would if we were using a simple metallic part. I think one thing that's becoming very clear over the last few years is that whereas 20 years ago composites were interesting materials that had some applications, there really isn't going to be any part of engineering which is completely unaffected by the use of composites. Composites are now basically the default material in large parts of aerospace. They're the default materials in wind turbine technology. Within 10 years, I suspect they will largely be the default material in automotive technology. They're certainly the default material in motorsport and the default material in high-performance vehicles. And with the BMW i3 and a series of other current developments, they're starting to become much more commonplace. So I think that if we are to meet the sort of greenhouse gas targets, the environmental sustainability targets, and develop more green energies, we're going to have an ever higher proportion of carbon fibre in engineering, which is going to produce a lot of new challenges. It's going to produce a lot of new research will be needed because it's still difficult to make parts cheaply and make parts well and make parts defect-free. But the good news, bad news here is that really people like me now, I'm going to be retiring in a couple of years' time, so it's really the next generation that are going to have to solve all these problems that we've left you with. I think it's unlikely that we will see completely new classes of material. It's certainly true that since the advent of composites, the world of metallics, both in terms of materials and in terms of processes for turning those materials into components, have very significantly improved. So you could, even if the only impact of composites was to improve the world of metallic components, all of the effort that we spent on composites would have been worthwhile. It's certainly true now that, for example, if you went back 30 years, motor cars were made of very low grades of steel. These days, ultra high strength steels are being used in cars, and that's at least in large part in response to the requirements to get the weights down, which would otherwise only be possible to meet with composites. 3D printing is an interesting technology. It's better known, really, rather than call it 3D printing, it's better to call it additive layer manufacturing. And you can take a view that composites is a version of additive layer manufacturing, insofar as we actually do build it up layer by layer. We don't use the same techniques as we do in additive layer manufacturing, where we lay things up layer by layer by layer, because we lay them over a curved surface. At the moment, additive layer manufacturing is a technology which is going, I think, to develop very well, but there are still big question marks about the structural integrity of parts that are being made by additive layer manufacture. The current problems that you have with certifying an aircraft, for example, you have to be able to prove a complete chain of understanding from the raw material through the process, to the tested part, to the part that goes on the aircraft. And it's actually very difficult to do that for additive layer manufacturing. The details of how the layers are laid down has a very significant impact on the mechanical performance, and to date it's not entirely predictable. There is a sort of an intermediate ground though. We currently have some developments in University of Bristol looking at how we can align short fibres. So rather than having the kind of continuous fibres that we had historically, we're taking fibres that are just a couple of millimetres long and aligning them extremely well. That allows us to do a couple of things. One thing is to do a complete closed-loop recycling of composites. So we could take a product at the end of its life, extract the fibres, break them back down to 2 millimetres and reprocess them into high-value materials. The other thing it allows us to do very interestingly is to produce effectively a bead or a wire that we can feed into an additive layer manufacturing machine, and that we can then steer very tightly over the surface. And I think in the future we will see the worlds of additive layer manufacturing and composites manufacturing starting to coalesce in some ways. It's probably the fate of the academic researcher to really never be able to clearly tell what effect they've had on the world until, very much later. There's a couple of books I've written on composite materials, one on resin transfer moulding and one on design of products. And it's very nice occasionally when you see them on somebody's bookshelf in industry, very well thumbed, damaged and used, that you think actually something that I've done might actually have gone out there, might actually have got used. I know there are parts of, the first half of my career was in industry rather than academia, and there's certainly components and materials and stuff that were developed at that part of my career that are certainly out there today flying around. So I suppose that's a benefit. Beyond that, it's quite difficult to be entirely clear of what one's impact is on the world. I suppose as an academic, one's principal impact on the world is probably actually the PhD students that go out and do all the things that you're no longer able to do yourself.
Would you like an expert voice on a specific field in composites? Let us know in the comment section below.